All right, I've had a few questions about binomial distributions this last week, and I sort of wanted to take a moment here and maybe just kind of play with a question. Hopefully it will help people broaden their understanding of these. We've hinted a lot about using a binomial distribution formula in Excel, and it's a great way to tackle these, but it also doesn't necessarily lend maybe as well to building your understanding. So I have a question here, or kind of a prompt maybe. It says, let's consider a student named Jonathan. That's me. If your name's Jonathan also, I'm not trying to pick on you. He has a quiz that he is not prepared to take. It doesn't sound like me at all. There are 5 questions on the quiz, and each one has 4 options. And I'm going to make the assumption here that only one of these is true, just to make things simple. If he just guesses, what is the probability that he gets all the questions correct? Now, that question isn't necessarily super crazy, but it's a good jumping off point for discussing this. And so, there's a few things that would take place. There are 4 questions on the quiz, and so the probability of getting it correct would be 1/4. So if you think about it like probability style, I think it's a 5-question quiz, and there are 4 options. The probability to get the first one is 1/4, the probability of the next one, 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 1/4. And this gives us 1/4 to the 5th, which is something. I don't know what it is exactly, but I'll use Excel here. So the probability of getting all 5 correct, we've done a little calculations here. We're going to say it's 1/4 raised to the 5th power, and that is this here. Now, if we used our binomial distribution, we have the probability of success is 1 out of 4, or 0.25. The number of trials is 5. And for this one, it would be a binom.dist. We'd have 5 correct out of 5 tries with a 0.25 probability of success. And then this is false if we're looking for the probability of this exact outcome. It's true if we want everything up to and including that. So here it is using a binomial distribution. And here is an answer to the question. Now, what about, and this is just for funsies, a little exploration of what happens if I miss. If I just get 1 correct, what's the probability of John just getting 1 correct? So if that happens, the probability of 1 correct, and I grab my pen again, let's say I got the first one correct, and then the rest of them are wrong. So there are 3/4, because there's 1 correct option and 3 wrong options. And so this is 1/4 to the 1st power and 3/4 to the 4th power. So we have 5 trials, and notice the exponents here. This is kind of ugly, but that's a 1 and a 4. They add up to 5. Now, in this case, this question has Jonathan here just getting the first one correct, but he could get the 2nd, the 3rd, the 4th, or the 5th. So there are 5 ways that we get it correct, and then there are the probability of each one is 1/4 to the 1st and 3/4 to the 4th. So notice if I do the probability of just getting exactly 1 correct, there's 5 ways I can get 1 correct. The probability of getting 1 correct, I'm going to use 0.25 raised to the 1st power, and then 0.75 raised to the 4th power. So again, kind of having some work here. 5 different ways to get this correct. Now if I use a binomial distribution, we have 1 correct out of 5 trials with a 0.25 probability of success. And then exactly 1 is just going to be false here, and we get that probability. Now, what ends up happening is if I get 2 correct, I could get the first 2 correct, I could get the second and third correct, I could get the third and fourth correct, I could get the fourth and fifth correct, I could get the first and last correct, I could get the first and next to last. Anyway, we end up with a lot of different ways we can get these correct, and that leads us to a combination, which I don't think we've talked about too much, but you might be familiar with the combination function. It has some cool formulas for it, but if we want to find the number of ways to get something success or something correct, anyway, we get a formula like this, and this is a factorial. So this is combinatorics. Again, if we have n things, so we have 5 things, and we are figuring out the number of ways, how many different combinations we can get one correct, we get this formula, and then it gets multiplied by the probability here if we want to build a system for it. So the binomial distribution does a probability formula that's really complicated, the P of x. We have the combination of n choose r, which is another way we can write this, times p to the x, and 1 minus p, or that's q, to the n minus x. And this is what the binomial distribution formula does for us, but we can kind of build it here if we want. Say I got an x and I can have 0 successes, 1 success, 2, 3, 4, or 5. My n here is 5, but I can find p of x using a binomial distribution here. Oops, binomial distribution. And I'm going to choose the input here as this. I'm going to say the number of trials is 5. The probability of success is 0.25. And I'm going to say false, because that gives me the probability of this exact one. Now, okay, this is 0 correct. Okay, and then we roll through here. We should see some numbers that we've seen before here. Oh, okay, here they are. This one and this one we've seen before, right? So we can sort of build this, and what it takes into account is all the different ways these outcomes can happen are just kind of built into this. So when we want like when we have questions that say at least this much, then you're kind of adding these probabilities. And if we use the true value, it'll be kind of a running total here. To get us to the overall probability. So we can kind of create a probability distribution, and you have some questions that ask you to do this. You can do it individually. Sometimes they ask you for a cumulative distribution, so you could just change here this to true, and it would add them up as you go. Now at 0, it's not that exciting, and at 5, it's really not that exciting necessarily, because we can do those probabilities using just old school probability rules. But I kind of think this is a little bit fun, something to play with. There were some questions asked this week about what if we have the probability that something does happen, and then the question asks us, what if it doesn't happen? Well, we can use the idea of the complement to figure those out and kind of think through this. So this is just what I was hoping might be a fun exploration to help broaden some understanding of where these all come from and what they do here anyway. But I also wanted to keep it kind of short. You won't really be tested on this, but you do need to know how to use the binomial distribution, and I'm hoping this increases understanding. So again, thank you for watching. I hope you wish you continued success as we move through this term, and I hope this brings some clarity and maybe a little bit of fun math exploration to your life.